So in our second part for confidence intervals for proportions, this idea, we're going to call it a one proportion z interval. You can see this up here. One proportion z intervals. So the critical value, we call C star, is determined by a particular confidence level. We call that C, that you specify. You always will either be given this, but this is what researchers do. They specify their confidence level. Rather than 1 or 2 or 3 standard deviations, we first decide the confidence level, say 95%, then find the number of standard deviations that will result in that interval. So we always are centered at our sample proportion, and then we work our way out. Okay, let's just see what this looks like in action with an example. So for me, take a look at this. Our first example of confidence intervals. A sample of 200 people indicate that 42% wash their hair every day. Interesting statistic. Find a 99% confidence interval for the population proportion. Okay, now for a moment, we're going to neglect checking the assumptions and conditions. I just want to start off with, we selected our confidence interval. So we first have to find our critical value. We call that our critical value. Our Z star for 99% is going to be, well, if we are 99%, well, what is not included in our distribution? So if we look over here and we look over here, well, that's 1% total. So what we're going to have to do to calculate this is go inverse normal of 0.995 because inverse normal only goes upper bound below. And then we're just going to do 0 and 1 because we are on our standard normal model. So on our calculator, I'm just going to go back. You know what? For our sake, we're going to go menu, statistics, distributions, and then we're going to go inverse normal. Our area is 0.995, 0 and 1. You hit OK, and we get 0.257583. As you can see, I have here. The next thing that we're going to do, and this is what you have to write, is that for a 99% confidence interval, we're going to write the sentence. We have p hat plus or minus z star times our standard error for our proportion. Now, in the problem, it said 42% say they wash their hands, plus or minus, this is our z star. Our sample proportion, that's p hat, that's q hat, over the square root of 200, gives us 0.42 plus or minus 0.0899. This, let's see in purple, this line gives us our interval. This would be where our true percentage of people that wash their hands is. So how do we interpret that? So based on a sample of 200 people, we are 99% confident the proportion of the population who wash their hair every day is between 33% and 51%. Now, all of this work up here is to walk you through how you should write out this by hand. Now, obviously, doing these types of calculations is a little more arduous. So let's show you how to do this type of test statistic on your calculator. So again, if I go to menu and I go to statistics, now what is right underneath our distributions? Well, that is our confidence interval. And for us, what we are doing is a one proportion z interval. Now, I know there's a lot of other options. We will talk about some of those. But one proportion, one prop, z interval. What we are going to say for our successes, this is where we have to do a little bit of work. So we have asked, that is our NP, our 200 times 0.42, which is 84. Our N was 200, and our confidence level was 99. So I hit OK. And then as I see on this printout, I get one prop Z interval, I have my lower level confidence interval, my upper level confidence interval. My p hat was 0.42, my margin of error, which is 0.089896, and n was 200. Huh, that's pretty nice. Okay, back to our notes. The determination of how large a sample we need to take is an important and mostly misunderstood step in planning any study. To determine an appropriate sample size, we must first choose how accurate you want to be. That's our margin of error. And how confident we want to be, and then how accurate you want to be. We can simply use the formula margin of error equals z star times the square root of p hat q hat over n, fill in the values we know, and solve for n. Or, if you need it spelled out for you, I've solved it for you. Don't memorize this. This is really not helpful, but it could be n equals z star squared times p hat q hat divided by the margin of error squared. So the formula requires p hat, which we do not yet have because we have not taken the sample. A good estimate for p hat, which will yield the largest value for p hat q hat. Think about it for a second. What would give you the largest number of p times q? Well, it's got to be 0.5. So in general, the sample size we need to produce a confidence interval with a given margin of error at a given confidence level, we say the margin of error is z star times p hat q hat over n. So n is here. So if we do p hat times q hat where it is 0.5, then it's going to give us 0.25. And so there, we get our z star, our critical value, and we have our margin of error squared in the denominator. And again, where z star is the critical value for the confidence level, which we find by inverse normal, that's our area, 0, 1. Remember, samples consist of a discrete number of data values or observations and cannot be decimal values. So round up the sample size you obtain, okay? I'm showing you this. There's going to be about like 2 or 3 homework problems that ask you find the sample size. This is the work that you got to do. So if you want to make note, this is on slide 28 of our notes. All right. Now, I'm not big into mnemonics, but the process for finding confidence intervals, there's a helpful way to remember it, and it is to panic. So the method to finding confidence intervals is to panic. Panic just stands for the parameter of interest. We're going to define it. What's our P? Checking your assumptions and conditions. That's our A. N, name the interval. I, write your interval, our confidence interval. And then C, conclude in context. So always interpret with a sentence, with a sentence, with a sentence. So P, let's just break it down one step at a time. P stands for the parameter. That is the statistical value of the population. P, represented usually by a Greek letter. So defined in the first step of your confidence interval, regardless on if it's for a proportion or for a mean. P, we stand for the true population proportion, let's say voting for proposition A. Mu, the true mean summer weight of the NFL players. The next thing we do, we check our assumptions and conditions. So this is our A in panic. We got to check for our random sampling condition, our independence condition. That means our 10% condition and our success fail condition. N, name the interval. Currently, we're finding Z intervals for a proportion, and soon we'll find other intervals for means or proportions. I is our interval. So this is like actually calculating it. So in this step, we're doing like a 1 prop Z interval. That's what we mean by naming it. And then doing the work is like stating out p hat plus or minus our margin of error. And then finally, once we do all of that work, we jump to our calculator and it does it for us. We give us our conclusion. And this is one of those things that, you know what? It's much better to just fill in the blanks. So I'd highlight this and just tell me. Based on the data from our sample size of n, we are C% confident the true value of the population proportion is between our lower bound and our upper bound. Wash, rinse, repeat. It's pretty nice to have those. So when stating the conclusion for a confidence interval, just use the following sentence structure. Just keep it simple. Based on the data from our sample size of n, we are, fill in the blank for your confidence level, blank % confident the true value of the population, whatever it is between our lower bound and our upper bound. So as always, what can go wrong? Know what we are actually doing. I'm trying to rephrase this a bunch of times, but you're going about collecting some sort of data. You get a sample proportion, and we're trying to figure out within a certain margin, certain interval, is our true population proportion within it. So the parameter, the true population parameter, P, does not vary. The parameter is a fixed value we are estimating. One sample is one sample. Other samples are equally valid and will return different intervals, as we saw with that computer printout. We rarely truly know the parameter, so do not state this with any certainty. It's always we use those squishy words, right? That's our squishy stuff. And remember, it's about the parameter, not the statistic, not p hat, but it's about p. So stick to your finding. Acknowledge that there's uncertainty, but remember that you chose the confidence. Treat the whole interval equally. Any values that fall within the interval are equally valid. So that first example, if we have an interval of 33% to 51% of people washing their hair, well, it could be 34% wash their hair daily. It could be 50.5% percent of the people that wash their hair daily. Both of those numbers are within our interval and are equally valid because we're talking about P, not P hat. What else can go wrong? Our margin of error is too large to be useful. I mean, think about it. We cannot be exact, but how precise do you need to be? If you make the margin of error smaller without changing the sample size, the result is the reduced level of your confidence. And that may not be a useful solution, right? If we're only 68% confident that our true population proportion is there, like if we're only 68% confident we're there, then it's not very helpful. So you need to think about your margin of error when you plan your study. So to get a narrower interval without giving up confidence, you need to have less variability. And just like we saw with sampling distributions, if you want to have less variability, what do you suppose you might increase in terms of figuring out accuracy? How do we narrow the interval without sacrificing confidence? And you guessed it. If you could read, we are increasing the sample size. So if you want to keep the same confidence interval, but reduce variability, we increase the sample size, which should make sense. Now, helpful things for using your calculator. If you're on TI-84, you're going to hit stats, then go over to test, and then scroll up to A, which is one prop Z interval. You're always going to type in X, which is the number of successes, N, that's the sample size, and then your confidence interval, and that's going to be a decimal. So X is going to be the number of successes, as we saw, which is just N times P hat. It's going to give you most of your information, provided that our methodology works. So let's do one example, and then we'll close out the notes. So your local newspaper polls a random sample of 330 voters, finding 104 who say they will vote yes on the upcoming school budget. Create a 95% confidence interval for actual sentiment of all voters. Concentrate on the conditions and the interpretation. Okay, so what do we know? 330 voters, finding 144, 95% confidence interval. So we're going to start with P, because we're going to do this. Let's get it in an actual color. P-A-N-I-C. So start with the parameter. What are we trying to find? We want a 95% confidence interval for the proportion of all voters in the population voting yes on the upcoming school budget. So what is the true feelings of the city? Next, we're going to check our assumptions and conditions. So it is reasonable to think that the responses were mutually independent. The problem stated that the voters were sampled randomly. How do I know that? It says a random sample, so we're good with there. Assuming there's more than 3,300 eligible voters in our population, I would say that 330 is less than 10% of the population of voters. But if we're in some small town in Michigan, 330 might be too big. Now, success and fail, if we go N times P hat, we know is 144, right? We were given 144 out of 330 said yes. So NQ would be 186. Because if you think about it, 144 plus 186 equals 330. Both of which are at least 10, so the sample size is large enough. So we've met our assumptions and conditions. Note, if you fail here, you stop. You don't keep going. So next up, what are we doing here? The conditions are satisfied, so I can use my normal model with our mean of 0.4364. If you're curious, this is 144 out of 330 with our standard error of our proportion, which is the square root of p hat q hat over n, to find our one proportion z interval with a confidence level of 95%. Now we got to do the work. So n is 330, p hat is 144 over 30. Our standard error is what we got. That's what we wrote above. Now we also need to know our 95% confidence interval. So that's our critical value. Remember, this is critical value, which goes inverse normal 0.97501, which is our 1.96. If you know this, just write it down. Z star equals 1.96. So I need you to calculate these. The margin of error is Z star times the standard error of our sample proportion, or 1.96 times 0.0273. So we get 0.0535. So this is our confidence interval, p hat plus or minus z star. Actually, this is just our margin of error. Our margin of error of our sample proportion, which gives us a lower bound of 0.3829, comma 0.4899. Now, how do we use the calculator to do the work for us? Again, we're going to go menu, statistics, and now we're going to go confidence intervals, one prop z interval. The number of successes was 144. The sample size was 330. Our confidence level was 0.95. We get our p hat, we get our margin of error, which gives us our sentence, and our lower bound and our upper bound. Now is our conclusion, which we are just going to fill in the blanks. Based on a sample of 330 voters, we are 95% confident that the proportion of voters voting yes on the budget is between 38.3% and 49.0%. One more example. An experiment finds 27% of 53 subjects report improvement after using a new medicine. Create a 95% confidence interval for the actual rate of improvement. So 27% of 53, which is 14.31 patients. Now, you can't have 14.31 patients, so we're going to say this is 15 patients at a 95% confidence interval. So we will find a 95% confidence interval for the portion of all people who will improve after using a new medication. Sounds useful. So this is our P. We establish our parameter. Here is our A, our assumptions. Independent. One patient's response to the medication should not have an influence on other patients' responses, so independence is justifiable. Random sampling condition. The patients were part of an experiment, which hopefully included random assignment of volunteers. 10%. In this instance, 10% is not relevant. We are testing the medication, and we certainly can't expect independence of treatment results. And then NP, which is 14.31, which means NQ is 38.69, both of which are greater than 10. Now, N, an experiment finds, so that's our prompt. So we should then, knowing that 27 of 53 is 14.31, we need our standard error. So that's 0.27 p hat q hat over n, which is 0.0610. Again, we're at 95% confidence interval, so this will help us find our critical value, which is 1.96. Great. So our margin of error is our critical value times our standard error for our sample proportion, 1.96 times 0.061, which gives us this value, 0.1195. So now we are going to assemble our confidence interval. The confidence interval is our sample proportion, p hat, plus or minus our margin of error. Or our lower bound is 0.1505 to 0.3895, or 15% to 39% roughly. So keep in mind the TI needs whole numbers for the number of successes. So if I was to go in and type 14.31, no bueno. So what I have to do is I go menu, statistics, confidence intervals, one prop z interval, number of successes. I'm going to tell you, round up. Our number of patients was 53, confidence interval. And we're going to get something slightly different, and that's okay. So if I round up, I get 0.161744 to 0.404294. If, for instance, I rounded down, so I can just say, for time's sake, type 14, I get 0.145456 and then 0.3828. Notice those are slightly different than what I found before. So personally for me, let's go back to our notes. Personally, I would use 14 as it's closer to 14.3, and it is the more conservative interval. So I'll accept either as an acceptable response, but just note, like, you're going to have to round if we're talking about proportions, number of patients. So finally, our conclusion. This is our C. This was our I. Based on a sample of 53 subjects, we are 95% confident that between the proportion of patients improving is between 15 and 39%. Now, I encourage you to read this last example. It is the same type of thing, just changing up the number. So I hope you get the point that when we are running these types of confidence intervals, we are going to state the parameter that we're looking for. We're going to check our assumptions and conditions. We're going to name the test that we're going to do. We're going to find the interval that we're looking for. And lastly, we are going to conclude our results. So this stuff, while be it new, it's some of those like wash, rinse, repeat things. You're going to get used to this thing over and over and over again. So hopefully I've given you a couple of good examples. If you have any questions, feel free to ask when we are in class. See you in the next one, Falcons.